Here we're going to look at a problem from the 2004 Putnam Exam. This is question B5. So if you recall, there are 6 questions in the morning. Those are labeled A1 through 6. And there are 6 questions given in the afternoon. So those are labeled B1 through 6. So the fact that this is B5 means it's like near the upper end of difficulty of Putnam type problems. And things can be at the upper end of difficulty for a couple of different reasons. They can be really tricky, or they can be really technical, or maybe a little bit of both. And I would say this is more on the side of being technical, although there will be some tricks involved as well. Okay, so our goal is to find the limit as x goes to 1 from below, so that's what this little superscript of a minus sign means, of the following infinite product. So we've got the product as n goes from 0 to infinity of 1 plus x to the n plus 1 over 1 plus x to the n, and all of that is raised to the x to the n power. Okay, so let's look at this. And keep in mind that we don't have a lot of good strategies for calculating infinite products until we turn them into infinite sums using the logarithm. And so that's what we're going to do. So we're going to look at the natural logarithm of this limit L. So let's keep in mind what that does. Well, first of all, we can bring it inside of a limit because the natural logarithm is a continuous function at x equals 1. And then it turns this product into a sum. And it also will bring this exponent down front as a multiplier and turn this quotient into a difference. So when all is said and done, we'll have the following object. It'll be the limit as x goes to 1 from below. Like I said, product turns into a sum. So we've got this sum as n goes from 0 up to infinity of x to the n. So see, the exponent came down as a multiplier. And then we'll have the natural log of 1 plus x to the n plus 1 minus the natural log of 1 plus x to the n. And again, we split that up into a difference from a quotient from some more natural log rules. Okay, great. Now, next, we're going to use the fact that an infinite series, this sum as n goes from 0 to infinity, is precisely defined as the limit of partial sums. So let's rewrite that as a limit of partial sums. So this is going to be equal to the limit as x goes to 1 from below, and then the limit as n goes to infinity of the sum as n goes from 0 up to capital N of x to the n times the natural log of 1 plus x to the n plus 1. And I'm actually going to factor this into 2 parts, which is totally allowed now that we have a finite sum. Then minus this sum as n goes from 0 to capital N of x to the n natural log of 1 plus x to the n, like that. Okay, great. Now, if we look at this, we see something interesting, and that is each of these sums is almost exactly the same. So notice we've got x to some power, and then the natural log of 1 plus x to the n plus 1, and then x to some power, natural log of 1 plus x to the n. So if we could make these exponents match like they do in the second sum, maybe we could do some sort of trick. And that's exactly what we want to do. So we can do that by multiplying this term by 1 over x, and that'll have the property of putting an x to the n plus 1 in there just by term multiplication. Okay, great. Now next, I would like to re-index this second sum so that the power of x looks the same as it does over here. That way we can combine these. So let's see maybe how we could do that. Well, we could do that by sending n to n minus 1. So if we send n to n minus 1, that's going to have the effect of starting at n equals 1. So that's because when n minus 1 equals 0, n equals 1. And then we'll end at capital N plus 1. But then if n is replaced with n minus 1, that means we just have an n in the exponent here, and we just have an n in the exponent here. So now if we look at our very first sum and our last sum look very, very similar. They just have different starting and ending points. But that'll be okay, because what we'll do is pull out the n plus first term here. So we'll extract the n plus first term from here because the second one doesn't have an n plus first term. And then we'll extract the 0th term from this second sum, again, because this first term doesn't have a 0th term. So let's see what we do when we do that. So we'll have the limit as x goes to 1 from below. We'll have the limit as n goes to infinity of, so this is going to be 1 over x times, so we'll have this sum as n goes from 1 up to n of x to the n natural log of 1 plus x to the n. So that's after extracting the n plus first term. But then we need to add the n plus first term back in. So that'll be plus x to the n plus 1 natural log of 1 plus x to the capital N plus 1, like that. Okay, good. So that's this first sum. So just to reiterate, this first sum expanded into that bit by extracting the n plus first term. Now we need to subtract what we get from expanding the second sum by taking out the 0th term. So notice the 0th term, that's when n equals 0. We'll have x to the 0, which is 1. Natural log of 1 plus x to the 0, so that's the natural log of 2. So we have minus natural log of 2, and then minus this sum as n goes from 1 to capital N of, let's see what it is, x to the n natural log of 1 plus x to the n. Great. So we have something like that. And I should point out that I'm missing an ending parentheses right here because this 1 over x should only be multiplying that. Okay, so now let's maybe combine some things. So what I want to notice is that this term right here and this term right here are the same, but this first one is being multiplied by 1 over x, so we want to keep that in mind. Okay, so let's see what we can do here. We can write this as the limit as x goes to 1 from below, and then we have the limit as n trends towards infinity of, so we'll have 1 over x minus 1. So 1 over x from what we get distributing this over to here, and then minus 1 just by thinking about this as being a coefficient of 1, times that sum, which is underlined in pink here. So we have this sum as n goes from 1 up to capital N of x to the n natural log of 1 plus x to the n. Okay, good. And then let's see what we have left over. So we'll have 1 over x times x to the n plus 1, so that'll be plus x to the n, and then the natural log of 1 plus x to the n plus 1, like that. And then finally, we've got this last term, which is just a number at this point, so the natural log of 2. Okay, now before we erase this and move on to the next board, what I want to notice is that as x is below 1, so it's between 0 and 1 here, given that the fact that we have the limit as x is approaching 1 from below, we're taking an exponent of x between 0 and 1 as this exponent goes to infinity. So what that tells us is that this term is going to 0 as capital N goes to infinity. But that means that this term is also going to 0 as capital N goes to infinity. So that means this whole bit is going to 0 times natural log of 1, which is equal to 0 as capital N goes to infinity. And again, that's because our limit is as x is going to 1 from below, meaning we can take these x values to be on the open interval 0 to 1. So let's see, that means all of this bit is gone. It just turns into 0. And we're left with this guy right here and this guy right here, which is just a number, so we can take it out of both limits. Okay, so let's maybe bring this up and then we'll keep going. Okay, so we ended the last board at the following spot. So the natural log of our desired limit is equal to minus natural log of 2 plus the limit as x goes to 1 from below of 1 over x minus 1, and then the limit as capital N goes to infinity of x to the n natural log of 1 plus x to the n. Now, I want to turn this back into an infinite sum instead of a limit of partial sums while we're at it. So in other words, I'll go ahead and get rid of this limit as capital N goes to infinity and replace this with an infinity because we don't need that limit of partial sums anymore. Okay, next what we'll do is start to expand the inside of that into a sum itself. So in other words, we'll have a double sum. So I want to first notice that this little guy right here can be written in the following tricky way. So this is going to be equal to the natural log of 1 plus y, where we're evaluating y between 0 and x to the n. And that may not seem helpful, but if you look at that as a 0th integral, then we can apply the fundamental theorem of calculus like in reverse to write that as an integral of something that has a nice geometric series interpretation. So let's maybe go ahead and do that. So here we have this is equal to minus natural log of 2, and then we'll have plus this limit as x goes to 1 from below. We have 1 over x minus 1. And then we'll have this sum as n goes from 1 to infinity of x to the n. Then like I said, I'm going to replace that pink underline with the pink part. But I want to do that, instead of writing it in that way, I want to write it with an integral. So that's going to be the integral of 0 to x to the n of the derivative of the natural log of 1 plus y. So that's going to be 1 over 1 plus y dy. So now that we've got that kind of thing. Now next, I'll use the fact that this 1 over 1 plus y has a nice geometric series expansion. So this can be expanded like the sum as m goes from 0 to infinity of minus 1 to the m, y to the m. Okay, good. Again, we're thinking about that as like 1 over 1 minus negative y, if you will. Okay, so let's maybe put that all together and see what we get. We have minus natural log of 2 plus this limit as x goes to 1 from below of 1 over x minus 1. And then we'll have this sum as n goes from 1 to infinity. And then next we'll have x to the n times the integral from 0 to x to the n of the sum as m goes from 0 to infinity of minus 1 to the m, y to the m, dy. Okay, good. But now what we want to do is essentially bring this integral inside of the sum, which we're allowed to do because we're in the region where this thing converges nicely, and take the antiderivative and plug in like the endpoints or whatever. So let's see what we get for that. So just to do this kind of off on the side, the integral from 0 to x to the n of y to the m dy. So this will be 1 over m plus 1, y to the m plus 1, evaluated from 0 to x to the n. So that's what we're going to replace this bit right here with. Okay, so let's see where that puts us. So we have minus natural log of 2 plus this limit as x goes to 1 from below. We have 1 over x minus 1. Then we'll have the sum as n goes from 1 up to infinity. And then the sum as m goes from 0 up to infinity of minus 1 to the m. So that's from this. And then we'll have x to the n. And then we'll have 1 over m plus 1. So that's from this term over here. And then y to the m plus 1 evaluated at x to the n. So that's going to be x to the mn plus n. So we have something that looks a little bit like that. Now, maybe the next thing that we'd like to do just to make both of these sums look similar is to re-index this so that this starts at m equals 1 instead of m equals 0. So we can do that by replacing m with m minus 1 everywhere. So that'll have the effect of starting at m equals 1. So that's going to put an m minus 1 here, but minus 1 to the m minus 1 is the same thing as minus 1 to the m plus 1. So we'll write that as m plus 1. And then here we'll have just an m in the denominator. And then that'll turn this into a x to the mn, instead of really m plus 1 times n. Okay, and now furthermore, we can multiply this x to the n and then this x to the mn back together to get x to the mn plus n, which is what we originally had. Okay, so let's maybe go ahead and bring that step to the top, and then we're actually pretty close. Okay, so we ended up at this spot. So we've got the natural log of our goal limit is minus natural log of 2, plus the limit as x goes to 1 from below of 1 minus 1 over x. Then we've got this sum as n goes from 1 to infinity. The sum as m goes from 1 to infinity. Minus 1 to the m plus 1, 1 over m, x to the mn plus n. Next, I want to notice that since, again, we can use the fact that x is on the open interval 0 to 1, because of our limiting setup, we can see that the convergence here is uniform. But since the convergence is uniform, we can exchange the order of summation. So let's do that. So here we have, this is minus natural log of 2 plus this limit as x goes to 1 from below. We still have this 1 minus 1 over x. Then, like I said, I'm going to exchange the order of summation. So I'll have the sum as m goes from 1 to infinity of minus 1 to the m plus 1 over m. I'll bring that m out because that doesn't depend on the n summation. Then we'll have this sum as n goes from 1 to infinity. Now I'll rewrite this as x to the m plus 1 all to the nth power. Great. And then that allows me to view this sum as a geometric series where my starting term is x to the m plus 1. That's because I'm starting at n equals 1 here. And then my common ratio is also x to the m plus 1. And then I can use the standard formula for the sum of a geometric series, which should be pretty familiar for tackling a problem like this anyway. Okay, so let's maybe go ahead and sum that series and see what we get. So I'll bring all of the rest of this stuff down. And then finally, we have this guy right here. Like I said, it'll be x to the m plus 1 over 1 minus x to the m plus 1, like that. Okay, nice. Now, next what I want to do is bring this guy inside and multiply it onto both of those terms. So let's see what that'll give us. That'll give us, in the numerator here, will be x to the m plus 1 minus x to the m. Okay, great. And then I'll have x minus 1. Okay, good. So let's maybe go ahead and bring that down. So here we have minus natural log of 2 plus, again, this limit as x goes to 1 from below. And then we'll have this sum as m goes from 1 up to infinity of minus 1 to the m plus 1. And then x to the m, x minus 1 over m times 1 minus x to the m plus 1, like that. So this is going to factor like 1 minus x, and then 1 plus x squared, all the way up to x to the m. Great. And so that's going to allow me to cancel this thing with this thing. That's going to pick up a minus sign, but we can get rid of that minus sign just by taking away one of the exponents here. So that'll go to minus 1 to the m instead of minus 1 to the m plus 1. And then next what we can do is bring this limit inside the summation. Again, that's because we have uniform convergence here. But then as x goes to 1, notice that this guy right here goes to 1. But then this guy right here goes to 1 plus 1 plus 1. But how many are there? There's m plus 1. So we have this is m plus 1. Okay, good. So when all is said and done, we're going to have this is minus natural log of 2 plus this sum as m goes from 1 to infinity of minus 1 to the m over m times m plus 1. So again, this cancellation right here changed the m plus 1 to an m. And then this factorization gave us this term that added up to m plus 1. Okay, so now let's bring that up and then keep going. So far we're here. We've got the natural log of our goal limit is minus natural log of 2 plus this sum as m goes from 1 to infinity minus 1 to the m plus 1 over m times m plus 1. Now we want to be inspired by the fact that integration and summation are pretty similar, so perhaps we could use a technique of integration to solve this, like partial fractions or something. So let's maybe take this 1 over m times m plus 1 and try to split it up like a over m plus b over m plus 1. Okay, great. So let's maybe clear the denominator by multiplying this whole thing by m times m plus 1. That'll give us 1 equals a times m plus 1 plus b times m. And then next, we can extract the constant term and the m term from both sides of this equation in order to find out what a and b are. So the constant term on the right-hand side is a, on the left-hand side is 1. The coefficient of m on the right-hand side is a plus b. Coefficient of m on the left-hand side is 0. So that tells us that b equals -1. Okay, good. So now that tells us that we can take this and rewrite it as minus natural log of 2 plus this sum as m goes from 1 to infinity of minus 1 to the m plus 1 times the quantity 1 over m minus 1 over m plus 1. Like that. Okay, good. Now next what we would like to do is to split this into two different sums. So we know everything here converges, so we're allowed to do that. So this is going to be equal to minus natural log of 2 plus this sum as m goes from 1 to infinity of minus 1 to the m plus 1 over m. And then the next one will be, let's see, plus this sum as m goes from 1 to infinity of minus 1 to the m. That's because minus 1 times minus 1 to the m plus 1 is minus 1 to the m plus 2, which is the same thing as minus 1 to the m, all over m plus 1. Now maybe we would like to put these two back together. So let's see how we can do that. So let's notice here that we're missing a first term. So in other words, we're missing a term where the denominator is equal to 1. So we can add and subtract that back in. So that's going to give us all of this with a plus 1 and then a minus 1. Like I said, we can group these two together and then put this plus 1 into this sum, and we will gain this first sum exactly. So that's going to leave us with minus natural log of 2 plus 2 times this sum as m goes from 1 to infinity of minus 1 to the m plus 1 all over m, like that. Okay, good. Now next, I want to re-index this thing so this starts at m equals 0. So I can do that by replacing m with m plus 1 here. So when m plus 1 is 1, then that means m is equal to 0. So that means now we have minus natural log of 2 minus 1 plus 2 times the sum as m goes from 0 up to infinity of minus 1 to the m over m plus 1. Now that may not seem super helpful, but if my sum starts at 0, I can use maybe techniques of geometric series to get this sum. So let's notice that this looks like the integral of a geometric series. So we could maybe write this as minus natural log of 2 minus 1 plus 2, and then we have this sum, m goes from 0 up to infinity of minus 1 to the m, and then this is going to be x to the m plus 1 all over m plus 1 evaluated from 0 to 1, where that x is not related to the x that we had previously. Okay, good, but now this looks like the 0th integral, which we could take the derivative and replace this with the first integral. So this is going to be the integral from 0 to infinity of x to the m dx. Sorry, from 0 to 1 of x to the m dx. So let's see what we have. So this is minus natural log of 2 minus 1 plus, now I'll bring the integral outside because we can do that in this case. Everything is nice. So we'll have 2 times the integral from 0 to 1 of this sum as m goes from 0 to infinity of minus 1 to the m x to the m dx. But now this is a nice geometric series that we've used pretty similar to it already. So here we have minus natural log of 2 minus 1 plus 2 times the integral from 0 to 1 of 1 over 1 plus x dx. So that's the sum of this geometric series. Okay, so let's notice that the antiderivative of this will be the natural log of 1 plus x. If we evaluate that at x equals 1, we get natural log of 2. If we evaluate it at 0, we get natural log of 1, which is 0. So we'll have 2 natural log of 2 from this integral minus a natural log of 2 will give us natural log of 2 minus the 1 that we already have here. So, but that's the value of the natural log of our limit. So that means if we exponentiate both sides, what we will see is that our limit is equal to 2 over e. And that's a good place to stop.